then. Okay, liquid CO2 on early Mars and why we should care about it. Dr. Michael Hecht, thanks for joining us. I'll let you go ahead and take it away.
Glad to at least virtually be there. This is the this material was the subject of a paper that came out about a year ago. I think I have a reference a little farther along with the authors listed here. And it's an idea that I've been sort of noodling over for probably about 15 years now. And when the Moxie project ended, I had some time to really think about it and move it forward. And we hope to move it forward even farther with if requests for funding will be successful. So I'd like to share it with you. But before I start, I am calling in from Hecht Observatory, where I've been on the staff for the last 13 years. It's a laboratory of about 100 people. It is not in Cambridge at MIT. It is on a much larger campus, almost at the New Hampshire border, that has about 100 people. We share it also with a comparable number of people from Lincoln Laboratory who use the site for the same reason, as a good site to put large radio telescopes. So there's a great deal of technology and science advancing astronomy, space and earth science being both geodetic science and atmospheric science. And among other things, we specialize in very long baseline interferometry, including the Event Horizon Telescope. And I suspect that probably maybe all of you have seen the image of the supermassive black hole, an M87 down at the bottom, that really was a project that originated here, and we are still a significant anchor of. That said, if you're looking for planetary science here, you're looking at it. That's almost entirely me. So part of the reason I'm reaching out for other places and other and colleagues elsewhere. Moxie is my usual topic. It formally ended a couple of years ago, but we're continuing to work on Moxie technology with a really exciting application for Venus. It turns out on Venus, what you really want to do is travel around in a balloon at between 50 and 60 kilometers, where there's sort of literally a shirt sleeve environment. And look at the surface, look at the winds, look at the air, and you can even measure tectonics. So Moxie produced oxygen on Mars and carbon dioxide. It ran for about 2 years off and on, really once every couple of months. It would run for a few hours. And it successfully demonstrated that you can make propellant-grade oxygen and breathing-grade oxygen rather reliably from the atmosphere on Mars. The reason for the interest in Venus is those same gases are buoyant in the Venus carbon dioxide atmosphere. So you can keep replenishing lost gas from a balloon and enable a long-duration ballooning. But other than what I just told you, I won't be talking about any of that today. I just wanted to touch base on it. Here is the topic of today is we all know Mars was warm and wet, right? Well, yes, we do, because we see all the features, all the lacustrine and fluvial features on the shorelines. We see aqueously altered minerals, and that pretty much nails it. It was wet, and if it was wet, it had to have been somewhat warm somewhere, so that you had something other than ice. And that's really where the community has been at for some time, even though it's difficult to understand how it came to be warm and wet. So there's enough of a head scratcher there that it's worth examining that assumption and saying, well, did everything we see necessarily come from liquid water? Or is there another alternative? And the only other alternative would be carbon dioxide. That's it's the other white meat. That's the other condensable gas. And carbon dioxide has a unique, we see it on Earth, Mars, I mentioned Venus, Titan, at the surface, and it has some unique properties on Mars compared to any of those places. On Earth, you don't find it condensed at all, with actually maybe very specialized exception down in deep ocean vents where you might actually have liquid carbon dioxide. There are some papers on that, but generally not condensable at the surface. On Venus, it's supercritical at the surface. It's certainly not condensable in the sense of liquid or solid. On Titan, it's condensable, but like on Earth, it's a trace gas. And only on Mars is it the dominant gas in the atmosphere and condensable, which means the atmosphere itself condenses out. And that's very, very different physics than when a trace gas, like, say, water on Earth, condenses out. The snow I see outside my window here. So that really is a hard thing to bend your mind around. And I'll show you why when I show you a phase diagram in a moment. But the point is that Mars is unique for having condensable major atmospheric constituent of a liquid that is ubiquitous on Earth. It's very common, but it usually comes in things like these little vials that we put in the saddlebag of our bicycles to pump up our tires in an emergency. We use liquid CO2 everywhere, but we don't find it generally in nature, again, with a couple of exceptions. So to talk about a major constituent of the atmosphere that is also condensable, we need to think about phase diagrams differently. I put a caveat in this because the purists will all say, wait, phase diagrams, those are partial pressures. And I'm kind of mixing it with total pressures here. And you can do that, and people generally do that on Mars because the atmosphere is almost entirely CO2. So the partial pressure and the total pressure are essentially the same thing. But with respect to the water phase diagram that I superimposed, for the other reason that really important things happen when even the partial pressure of water equals the atmospheric pressure, and that would be called boiling. Or, if we're down here, that might be called explosive sublimation. And in practice, then, that total pressure of the atmosphere puts a limit on the temperature, and then hence the phases of both CO2 and H2O. Now, in the case of H2O, you can go anywhere in this diagram below that atmospheric total pressure, which is not allowed. You can go anywhere in that diagram with the liquid phase, more or less independently of the exterior conditions, in a non-equilibrium situation. But CO2 is different. In CO2, if you have mixed phase, for example, today you might have solid CO2 and gaseous CO2, that can only happen on this phase boundary, on the line. You can't go left, you can't go right. On the phase boundary, to go left, you would have to condense the entire atmosphere. To go right, well, you can go right, but you would have to sublimate the entire solid inventory to go right. And that's what happens on Mars today. On Mars today, modern Mars, if you go to the poles in the winters on the respective poles, you'll see condensed CO2 at 148 Kelvin. So you'll be down here at 148 Kelvin, plus or minus a little as the atmospheric pressure changes, as you literally condense out about a third of the atmosphere. But it's right around 148 Kelvin, and you can't move off that phase boundary until you evaporate all the condensed CO2, or that is the temperature. And that's a really important rule that would apply equally well to a putative, hypothetical early Mars, where under some circumstances you could get liquid CO2. Again, you would have to exist right on that phase boundary for a certain total pressure of the Mars atmosphere. There would be a certain temperature that any place on the planet where there was liquid CO2 would have to be at that same temperature, isothermally. So given that constraint, here's the dilemma. We think we know that there was liquid CO2, liquid hot water on early Mars. We think we know that. Okay, there's the triple point, 6.1 millibar, right about where we are today, 273 Kelvin. So pretty easy to imagine that you have much higher pressure than that. And typically the postulate is 1 to 3 or 1 to 10 bars, depending who you read or what you read. And the condition, because of the shape of the space diagram, the condition for melting, unless you have very salty brines, is you need to be over 0C. You need to be over 273 K. That is extremely unlikely on early Mars. Okay, it's not impossible, and I think the general assumption is it must have happened, but it would require other greenhouse gases other than CO2 in the atmosphere. People have speculated a lot about that. Maybe some other phenomena, ice crystal clouds have been suggested. But if the blue represents what we think the conditions were likely to have been in early Mars, getting up here where there was liquid water seems pretty unlikely. Getting to liquid CO2 planet-wide, in other words, getting up to the conditions where you could walk out the door and see liquid CO2 requires getting above 5.8 bar. The temperatures seem reasonable. The pressures seem somewhat high from what we know about the CO2 inventory. But I would argue that getting up here to liquid CO2 is is no more unlikely than getting up here to liquid water. Okay, I'm trying to make a very modest statement. And then point out a disparity. The disparity is we've studied this a whole lot because we assume this is where early Mars was. And basically nobody has studied this option that, gee, maybe the pressure was a bit higher than we thought. And I'll make one other point about the phase diagram, which is given that a two-phase solution is pinned to that boundary. Okay, the only question of whether you could have had that much pressure at a given temperature is simply a matter of inventory. If you have enough inventory to make 6 bar pressure and it warms up above 220 K, you will have 6 bar in the atmosphere. You can't hide it. You have to be on that phase diagram if you're going to have two phases. So,
Mike, quick question.
Yeah.
Can you say again, what is the blue kind of gradient there under early Mars in that?
Yes, good question, man. I neglected to say that. That's kind of a notional, is the word I'm looking for. That's a notional idea of where we think the temperature would have sat at different obliquity periods, at different at different parts of the obliquity cycle, day, night, etc. Mostly it's cold. The point is Mars is mostly cold. The models tell us that the pressures at which it's possible we might have gotten up to melting, which is this vertical line, are going to be around the 1 to 2 bar range, not the 7 or 8 or 9 bar range. This goes back to Jim Casting and a lot of the models being done. So it's a notional idea where the darker blue is more likely that was the temperature most often. That was the pressure most often.
Okay. And yet you were saying that you thought it was equally likely that liquid CO2 or liquid H2O would be present.
I'm saying that only because from what we know,
yes,
this isn't terribly likely. And I think most people would argue we haven't, and maybe I shaded this a little more darkly at high pressures than I might have. But most people would argue that we haven't identified 5.81 bar worth of inventory yet. Now, the thing about inventory is you're always finding more, right? So you see articles that say, oh, all these clays, they can represent a reservoir of CO2. Maybe the seismometry data from InSight is pointing to possibly, subsurface oceans, and they may also be reservoirs of CO2. There's a lot of evidence for very deep layers of carbonates that are exhumed by craters in the south, and we don't know what that inventory is. So it's not going to get smaller over time; it's going to get bigger. I don't want to make. I don't want anyone to think I'm arguing that Mars was never wet. What I'm arguing is that maybe it was, maybe it was liquid CO2, maybe it was both.
Right.
But we got to look at this because we haven't. And I think the same thing with the shading on modern Mars. Modern Mars is, and it's worth a comment on this, modern Mars is mostly cold. It's mostly in a narrow pressure range from 6 to 10 millibar, depending, a lot on your elevation, someone in your latitude, obliquity cycles, etc. And certainly you find surface temperatures that get up here to 0C and warmer, but their surface temperatures of very low thermal inertia stuff, and that's important. So you can find, fluffy dust that gets up to 300 Kelvin, and you see it if you look at the temperatures on the surface. You're not going to find a chunk of ice to get that hot because there's enormous diurnal temperature swing. And the low thermal inertia materials can follow it and get quite warm in the daytime. Something like ice, particularly with the latent heat of phase change, is not going to get anywhere near those temperatures if it were exposed on modern Mars. Let me stop and see if there's questions about this, because phase diagrams, I've gotten into long sort of, hours-long discussions about what phase diagrams really mean. And frankly, this idea of the dominant phase condensing has made my head hurt more than a few times. Everyone good with that?
Everybody's good, I guess.
Everyone's good. All right, let's move on then. And to why this is even interesting. I had thought about this. I remember I first thought about this at an LPSC meeting, and I was listening to a theory section and talking about how the heck you make it warm enough for liquid water. And at the time, I had been thinking a lot about CO2 phase diagrams for a MOXIE-related reason, and kept thinking, gee, what they're describing is more like liquid CO2 conditions, but what about the aqueous alteration? And I realized, since I also was thinking a lot about electrochemistry at the time, that it doesn't take much to have water reactions in liquid CO2, even though liquid CO2 has very, very, very small solubility for liquid water. When you actually look at water itself, the stuff that's reacting is typically the hydronium and the hydroxyls that are measured by the pH, and they're also orders of magnitude, lower in concentration than the unionized water, and that causes lots of chemical reactions. So if the water tends to be ionized in liquid carbon dioxide, I was thinking at the time, I think this is wrong in hindsight, you could get the same kind of chemical reactions in liquid CO2 as you would in water. And that idea, just kind of percolated in my brain for quite a few years, until one day I just stumbled on the paper here by Brian McGrail's group out of PNNL that was titled "Water Reactivity in the Liquid and Supercritical CO2 Phase. Has Half the Story Been Neglected?" which was exactly what I had been thinking about for Mars. This has nothing to do with Mars, which is why it took me so long to stumble on it. So again, it's out of Brian McGrail's group. So I started thinking about this as the Holy McGrail for, for the liquid CO2 story. And they do a number of experiments, but the one that I think is most visually striking is plain old steel, iron. What happens to steel when you put it in liquid carbon dioxide with water on the bottom? Because at supercritical temperatures, water sinks. And this is subcritical, but it's nearly critical. And CO2 floats, and you see that you get lots of carbonation, lots of siderite forming in the liquid CO2, but not in the water, much more than in the water. So my goodness, liquid CO2 is a much more aggressive medium in this instance for alteration than plain old water is. Now, I qualify that by saying all this work is at room temperature and above. And, there's been a lot of studies since. I'll tell you why in a moment. And the thinking now is that thin interfacial films of water are probably involved, not just the water that's dissolved, but the water that is diffusing through the liquid CO2, assisted by the fact that the viscosity is really, really low in liquid CO2, meaning that the diffusivity is really, really high. So water can just pass through it like it's not there, and it tends to go to the interface and settle into two-dimensional films, which have a very, very high reactivity rate with the surfaces. Why are people studying that? And the answer is that we're putting a lot of investment, a lot of funding into carbon capture, and sometimes just carbon capture from the atmosphere, with the thinking that now we have big reservoirs of CO2. We have to put them somewhere. We can try to react them out, which takes a lot of energy, or we can just bury them. So there's been a lot of thinking about burying deep underground, where the pressure would naturally condense the CO2 into liquid CO2 and eventually form carbonates with the surrounding rock walls. So people have been looking at how does the liquid CO2 react with rock walls, react with cap rocks, react with pipes, react. That's the reason they're looking at steel. So all of this research has been done in the context of sequestration of liquid CO2 on Earth. And which is great because it gives us a leg up in thinking about Mars. The difference being that, this all happens at temperatures that are room temperature and above, approaching supercritical. Did I mark supercritical on here? No, I didn't. But that are, many tens of bar pressure, not at 5 or 6 bar pressure at temperatures you can see here of, under just a little bit under 200. No, sorry, just a little bit under 220 was where it start getting liquid carbon dioxide. So, certainly sub-zero temperatures, which means at temperatures where the water would be frozen. Does this work at low temperatures? Do the Arrhenius constants or the rate constants kill the reaction? Does the water ice versus liquid water kill the reaction? I'm not too worried about the ice. I don't know about the rate constants. Nobody knows. So the point is, there's a lot of supportive ideas that this reaction may, in fact, happen at lower pressure and temperature. We don't know. And fortunately, the bad news is we don't know. The good news is that it's easy to find out. We just haven't done that yet. So anyway, let me talk about the specific reactions that are relevant to Mars. You get carbonates, of course, everywhere. Having liquid CO2 available and water available is a perfect recipe for making carbonates. They're ubiquitous. I list a number of case studies that have specifically been seen. Anthracite, forsterite, phlogopite. I'm not a geologist, so forgive me if I'm mangling these. Calcite, aragonite, also silica, by the way, et cetera. So you get, kaolinite. I know that that's been seen on Mars. A number of different, odd and interesting carbonates form in different experiments. Interestingly, you also see phyllosilicates forming, and limited experiments, including that first McGrail paper, added H2S to the liquid CO2. And they didn't do surface analysis, unfortunately, but they said, gee, we added H2S and there was extensive uniform corrosion over the entire surface, dark precipitate everywhere, some indications of white precipitate in spots. I think that's very good indication they were making sulfates. And there are subsequent indications as well in other experiments. But again, they were not thinking about Mars, and they were mostly thinking about carbonates because they'd like to ultimately bury the sequestered CO2 and have it stay there. So I just want to throw in one more because I know there's some kind of interesting and head-scratching rock coatings and veins and patches that have been seen on Mars of manganese. And where does all that come from? And one of the experiments that have been done has been to look at what happens when you add manganese chloride to the water solution. And indeed, you get lots of bright orange, pretty rhodochrosite oxidation in in veins and near the interfaces with water. So I just threw that one in as a curiosity. There are many other reactions. And so the point is that a lot of the things that we have seen that we have assumed are uniquely water. Well, yeah, they are uniquely water, but they can be conformed in a liquid carbon dioxide medium. And at least at high temperatures, they can be formed more readily than in pure water. So on Mars, well, I think first we have to start with an assumption that there's lots of water on Mars. So anywhere there was liquid CO2 would likely have been water saturated. And that's assuming that where you have an ice liquid CO2 interface, water ice liquid CO2, that the molecules of water in the water ice can migrate into the liquid CO2. I think there's lots of evidence that happens. Not only that happens, but even there are very low temperature experiments with ice and clays, for example, where people see liquid, two-dimensional liquid water films at the interfaces at minus 70 degrees. So I think that's probably a good bet. It's one thing that needs to be tested. Um, I mentioned the rapid diffusion. Now, liquid CO2 is not a good solvent in general, with the exception of organics, but water does make it a better solvent. That's another issue. It's what's called a polarity modifier. One of the mysteries on Mars in terms of aqueous alteration is you see what seem to be incompatible minerals, fluorapatite and jarosite, in the same place, whereas one forms in a condition that would dissolve the other. The jarosite forms in an acidic condition that would dissolve the fluorapatite. The fact that LCO2 is not a good solvent might explain how you get some of those combinations. But again, tens of fresh bar pressure, elevated temperature, and most studies of a supercritical CO2 at many tens of bars. Some are subcritical. And then the question is, will this happen under cold conditions? And we need to find out. Another caveat I added is that going through all these studies, because they're not intended to inform us about Mars, requires multiple readings and a lot of thought, because many of them were put in a configuration where they assumed the water was there first. They were adding the liquid CO2 and then asking what the infusion of CO2 into the water, making Perrier, right, would do in terms of reacting out the CO2. Some of them were done in the configuration we're interested in, where you have water on one side, or ice, then liquid CO2, and the sample in liquid CO2. That's the smaller set of studies, including the one I showed you by McGrail. But where the two overlap, they seem to give the same result, which supports the thin film hypothesis. And so I think we can learn from these more ubiquitous liquid CO2 brine sample experiments than we might have originally thought. Anyway, so I mentioned, so first of all, I've always been a little puzzled at all of the minerals we see on Mars that form in acidic solutions, because what's puzzling me about that is that if you're under a thick CO2 atmosphere, 1 or 2 or 3 bar, whatever's necessary to make liquid water, it's very hard to move the water itself off of pH about 3.4. Okay, just by the nature of the solubility of CO2 into water, and the fact that that CO2, bicarbonate, carbonic acid, transitions are a pH buffer. So to form things in acidic solutions is kind of a head scratcher, and maybe it forms underground or under other conditions where that atmosphere isn't constantly saturating the solution, but it's still a mystery. The pH incompatibilities I mentioned, I give a few examples here. And then note that pH is kind of a meaningless concept with liquid CO2, although if there are thin water films, maybe it's not so meaningless, but for the liquid CO2 itself, it's meaningless. So you get reactions, but you're not going to get a pH relationship the way you do with water. And then there are other products. If you look at some of the diagenetic analyses of things found on Mars, that it's not even sufficient to get to 0 C. You've got to get up to tens of C to form them. And that's even harder to explain, because even if you can wave your hands and explain how you got to 0 C on Mars, in places where there is ice, getting past the ice to water transition to the point you can raise the temperature above 0 C, that's really tough. That means all the ice has to be melted into water before you can even start pushing above 0. So hard to explain. And then again, I tossed in the manganese oxide because I find that kind of intriguing. And you can make manganese oxide from manganese carbonate in plausible ways. So question is, coming back to the liquid CO2, I've been talking about how it's challenging to make water. Under what scenarios might we get liquid CO2 on Mars under conditions that are plausible on early Mars? And I've looked at 3 such circumstances. The most appealing one, in many ways, the most satisfying one, I should say, is that you just reach 5.18 bar and you get above your 220 C and you have stable surface liquid carbon dioxide. Everywhere that meets the isothermal requirement. So the way to think about that quickly is, right, look today at where you might get condensed solid CO2. Same argument for getting condensed liquid CO2. It has to be somewhere isothermal. It doesn't have to be at the point of the pole. The second case is whether you can get basal liquid CO2 beneath ice sheets, whether those ice sheets are carbon dioxide or water. And the issue there, just quickly, is that one shouldn't confuse hydrostatic pressure or lithostatic pressure with fugacity. As Bruce Stokowski once pointed out to me, he doesn't remember this. It once pointed out to me is that, got the people working in the office on the first floor of the Empire State Building aren't being crushed, right? And as long as there's gas connection, the gas underneath a pile of regolith is not at any higher pressure than it is at the surface, other than the scale height changes. So, but beneath ice sheets, you have a different story. You may have captured, trapped reservoirs of liquid CO2. And then the third case is subsurface liquid CO2 aquifers. And I'll talk about all three of these briefly. So let's start with stable surface liquid CO2. This would be a high obliquity phenomenon when in the sense that we want high atmospheric pressures. That's when you're most likely to get them, when the atmosphere isn't all collapsed. So if the pressure was sufficiently high, greater than 5.18 bar, you'd have CO2 rain, rivers, lakes, melting CO2 snow, all kinds of phenomena you associate with liquid water. There's very little empirical evidence, of what that ultimate pressure was on early Mars, other than attempts to catalog the inventory, and those attempts come to, well, we can account for a few bar, right? So, if we're within a factor of 2 of where you need to be, and I would argue that the factor of 2 is fairly small. Bruce Stokowski also did a couple of good reviews. Maven certainly doesn't see anything like that, but he did some reviews of, okay, if the escape to space is a small fraction of it, where's the rest? So losses to space are a small part. Buried CO2 ice deposits are actually a larger part. Possible deep carbonate deposits are an even larger part. And again, we see those exhumed in craters. There's things like reservoirs in clays, near surface clays, et cetera. And of course, the pressure has to be extremely elevation dependent. So the idea here is you simply populate this dotted portion of the phase diagram. Simple, straightforward. Okay, so that's the stable surface. So to emphasize again, any place with condensed phases must be isothermal at a given elevation. But first of all, even today, you see CO2 ice down to latitude 34. Theoretically, you could see it down to 22. I think Norbert may have done that calculation. And that's at, and then when you get to a higher obliquity, you get much more uniform temperatures. So in fact, it could have gone much lower than 22 degrees. And in addition, just because we find something at 10 degrees latitude doesn't mean it was formed at 10 degrees latitude. There's another 10 degree of uncertainty due to, polar wander as to what latitude it formed at. So in other words, we might well see evidence of liquid CO2 just about anywhere on the planet, including low altitudes, if we had pressure above 5.18 bar at one point. So the isothermal requirement is tricky, but I think is not limiting what we might see today. And the purpose, I think, of all, it should be emphasized, of doing laboratory work, of understanding this, the goal, the real goal is to identify characteristics of the altered products that might uniquely identify them as liquid CO2 origin rather than liquid water origin. So if we can start to identify and say, hey, this mineral here, this was formed in liquid CO2, we can start answering some of these really interesting atmospheric questions of where were pressure and temperature conditions such that this could have formed. So there's, there's a lot of leverage in understanding early climate if we can start identifying mineralogy that may come from these reactions. So the second case is if you bury it. And Peter Bueller gave an interesting talk about water uh, recently at the Mars Polar Science Conference, and it was published not long afterwards, where he's pointing out how there may have been, glaciers of water ice with liquid underneath formed from the hydrostatic pressure. And I looked at that and said, well, if that's the case, then you're also going to form liquid CO2 for similar reasons. But the basic model looks like this, that if you get something like 100 meters deposit, now this is at low obliquity when the atmosphere is collapsed. If the atmosphere is collapsed, the aha moment, this is almost embarrassing, that the aha moment for me was realizing that if you collapse the atmosphere, you haven't changed its weight, right? It weighs just as much on the ground as it does in the air. You've just changed its distribution, right? So you put most of it down at high latitudes, but it's the same weight of column, and therefore it creates the same pressure underneath it. But for that pressure to not equilibrate to now the very low atmospheric pressure, it has to be sealed. So if you get a big mound or a sheet, more likely, of condensed solid CO2, you go down as little as about 100 meters, and you're going to get the pressure conditions compatible with liquid. And the only requirement for that to stay liquid is for that to be in an enclosed volume where the pressure can stay high. And what's likely to create that enclosed volume, in my mind, is permafrost, which is going to form underneath it at those temperature conditions. So you might imagine permafrost, regolith, liquid, and then the solid CO2, which then forms a cap over the whole thing. And while I show this as a mound, this could be a sheet that extends for hundreds and hundreds of kilometers or more. So I think that's a plausible scenario for getting liquid CO2. Again, remembering lithostatic pressure and gas pressure are not the same thing. On the phase diagram, it looks like this, that what's happening is that here's your boundary. Because you're inside the solid, you can go past that phase boundary this way. You get to about 100 meters of CO2, of solid CO2, and the pressure gets up here, and that's where you get a liquid core. Okay, so that would be what this would look like on the phase diagram. And I point out, Mike Mellon pointed this out some time ago, that the thermal conductivity of CO2 is 5 to 6 times smaller. In other words, it's a better insulator by factor of 5 or 6 than water ice. So the temperature increases as a result of the geothermal gradient much faster in solid CO2 than it does in water ice. So that's why it only takes 100 meters or so, because there's a much larger gradient than you might expect. Okay, third one is, I can't give this talk without mentioning aquifers of subsurface liquid CO2 because of all the hubbub back in 2000 with Nick Hoffman first proposing white Mars, other people following it up with other papers, and including Steve Squires and Jules Goldspiel and others, suggesting that maybe you have these aquifers of liquefied CO2 that burst open and form valley networks and other structures. I think that's not likely. Sarah Stewart, Stewart and Nimmo in 2002, argued against this, and they pointed out that, just arguing that these subsurface high pressure zones are unlikely, that again, it wasn't clear that in this work that the distinction between lithostatic pressure and fugacity was being respected, and sealed volumes were necessarily being assumed. So it's possible. And the work, I thought, did a really nice job of drawing attention to some of the problems with the warm-wet scenario. But and also, in my mind, it didn't gain traction because it still didn't explain aqueous alteration. So you're looking at this and said, yeah, okay, maybe you can explain a riverbed this way, but how do you explain all these altered rocks? How do you explain the phyllosilicates? How do you explain, the sulfates? How do you explain the carbonates? So I think what we're offering here is, yeah, okay, you can explain that too. So 3 models, one of them may have worked. I can show you how this one would work. The idea again is that you have some constrained, some constrained CO2 that increases in pressure, goes up to the liquid boundary, and then something breaches and there's an explosive release that follows this phase boundary back down to here very quickly. And so I think it's described in Nick Hoffman's work as simultaneously freezing and boiling. But basically what it means is that you're running down the phase diagram boundary once it's exposed to the atmosphere really quickly. Okay, so I've waved my hands a couple of times at why even bothering looking beyond warm, wet Mars. A lot of this goes back to Jim Casting in 1991, pointing out that, the faint sun hypothesis, or the faint sun paradox, if you like, in the days, in the epochs in which there was supposed to be liquid water, if you actually do the models, you don't see a warm enough surface under any pressure conditions of CO2 that would be consistent with crossing that 0C boundary. Okay, so that's the main reason. And the Casting paper kind of concludes that the same way we know it must have happened, so maybe we should look at other greenhouse gases. It also it did have a paragraph saying, what about liquid CO2? And oddly, it concluded, no, under 6 bar pressure, it would be too cold even for liquid CO2. I would argue that isn't a worse problem than the liquid water problem, and it shouldn't have been dismissed so readily. So I mentioned, the climate models are a problem. The pH inconsistencies are a problem. And so adding an additional low temperature pathway would explain some of these anomalies. I probably, given the time, I want time for discussion. Won't go too much into this, but you can look at seasonal deposition, rather than residual deposition. And today, if you look at the poles, you can do a back of the envelope calculation that tells you take the length of the winter, put in the latent heats, and you'll get and the density of solid CO2, and you'll get a calculation of about 1.6 meters forming. If you had walked up the phase diagram to having the bars of pressure, so the temperature was 220 K, which is what you need for liquid CO2, you would have had something like 16.3, 10 times as much deposition from the fact that simply the radiative heat loss from at 220K is a lot bigger, T to the fourth, than at 148K. The fact that doesn't work because, at that point you have weather and you don't necessarily have good coupling, radiation coupling of the surface to space. You might have a warm sky, but it's a place to start. And by the same way, that 16.3 meters doesn't really make a dent in the 6 bar pressure. It might make a 20 millibar dent. Okay, morphology. I think this is the last major subject. Physical properties of liquid carbon dioxide. Well, other than the curiosity that CO2 ice, that solid CO2 sinks, unlike water ice on water, but water ice will float on liquid CO2. And the important thing, as I mentioned, is the viscosity. Now, this affects the diffusivity from a chemistry point of view, but it also affects the way that the liquid CO2 might interact with the surface if it were flowing. So it means very low surface tension, okay? And low viscosity may mean high velocity flow. So if I were to kind of put all this together and say what liquid CO2 might look like, you might say that you'd tend to see long, heavily silted channels because the lifting of material from a riverbed is determined by the basal shear stress, and that's a function of velocity and density. And you might ask, does low viscosity, lead to high velocity? I would expect it would. And at the same time, that leads to high Reynolds numbers, more turbulence, which facilitates lifting of the silt. The higher density of liquid CO2 compared to water would keep the particles in suspension. And so all of this together is, why you might get these long, heavily silted channels. And I use that terminology because, in fact, we do tend to see long, heavily silted channels. There was a nice paper by Kite et al. In 2019 about this and pointing out that the late run-up channels, the modern ones, are found predominantly at lower elevations. They're wider than expected. They lack braids and boulders. And I also point out, they were concerned that um, they don't know where the energy is coming from melting the snow. And wanted to point out that you don't need energy to melt liquid CO2 because it sort of simultaneously phase separates into gas and liquid such that the delta E is zero. It takes no energy. You gain some energy from from the melting and lose some energy from the sublimation, and it all balances out. So it can happen quite quickly and without energy input. So in other words, suppose there was an obliquity swing, you get a late high pressure epoch followed by a rapid atmospheric collapse. You'd make a slow line, and the snow melt would result as the snow line moved up, onto the mountains. So there are some scenarios that might give you, might match some of the morphological observations. And I have to, of course, mention life. Astrobiologists I've talked to are surprisingly receptive to this idea, maybe because they're just tend to be receptive to out-of-the-box ideas. I would have expected they would be unhappy with it because liquid carbon dioxide is an excellent solvent for organics. Okay, so anytime you might try to get organic to form, it's going to nicely dissolve the organics. But actually, Kirk Schultz-McCook has written on this, as he has in many unlikely scenarios for water, and actually has a paper on it. And they come up with a scenario that allows for supercritical CO2 as a medium for life. So there's at least one paper on the subject. And the other thing that my friend Max Coleman pointed out is that while liquid CO2 might be bad for life, it might be a very good way to concentrate organic residue in that we might find, in terms of from a research perspective of leaving back a detectable residue of what ancient organics might have looked like. So it might be a experimental advantage, even if it's bad for life. So the next steps, again, the good news and the bad news. The bad news is we don't know enough to know if this was plausible. The good news, it's not so hard to find out. So laboratory studies, you simply do the same studies that were done at high temperature, you do them at low temperature. I'd also love to see some atmospheric modeling, and I think some of this has been done to determine the possible latitude and seasonal range of liquid CO2 on the surface, and that's an analogy to papers that have looked at the extent of solid CO2 on the surface at past obliquities. And again, I think Norbert, who's on, I think has done some of that, if I remember correctly. Reactive transport modeling, I'd also like to see some chemistry modeling associated with these reactions. It's starting to be done for sequestration studies. It could be done for Mars conditions. So I think those are all important steps. They all start with funding and money. And in conclusion, I can't say this enough, a dose of caution. We don't know where all the CO2 went, either for the warm, wet scenario or for this scenario. And until we find it, we're all, again, scratching our heads. We don't know where the carbonates went, again, for both scenarios. There should have been carbonates. We don't see them. There's indications there's a lot of them that were buried quite deeply. I can imagine liquid CO2 might have something to do with burying them deeply if the CO2 were able to percolate downward as a liquid and before it reacted. We don't know how fast the reactions go at low temperature. We need to find out, or if they go at all. And again, the caveat that it's not an either or choice. It's just another arrow in the quiver. Bottom line, laboratory studies needed desperately. So I think I will conclude with a kind of cringy takeoff on John Lennon. Imagine there's no water. It's easy if you try. CO2 below you and raining from the sky. I won't sing it. Imagine thirsty microbes living day to day. Thank you for your attention, for an open mind, and any questions in the remaining time I'd be happy to address.
Thank you, Mike. This is great. Um,
Hopefully thought provoking. I
it's
love
very
this kind of
thought-provoking
problem.
and
So,
provocative. Um, can you go back one slide, please? I just wanted to absorb the we don't know all the carbonates. Okay. And so I'd encourage everybody to raise your hands with questions. We do have a few minutes for questions, but I guess one thing I was wondering about these things that are still sort of thing topics to go back to follow up on. Do you have a plan for that? Is this something that you're kind of still working on then, or what's your status?
well, Isaac and I have I don't know if Isaac's on, but do have a proposal in,
Right.
I think Darby's part of this, to the new SSS program to do the laboratory work. To do the
Just for lab.
laboratory
Okay.
work, there's only one, it's basically straightforward with one small wrinkle. It's like if you want to explore a range of conditions, so you can look at rate constants, you'd like to have a pressure vessel that'll get up to about 50 bar. That's pretty trivial. You'd like to have a freezer that'll get down to minus 50. That also is just something you buy. To buy a pressure vessel compatible with minus 50, that might be a little harder. Okay. So it's all commonplace stuff, but it might be not commonplace environments.
Okay. Norbert's got his hand up.
Um, yeah, so hi Mike. So
You know,
how long into Mars history do you imagine this liquid water lasted? I mean, it's much easier to imagine it for early Noachian versus the Amazonian, right? Um, how long should it have lasted?
how long should which have lasted? The liquid CO2?
Yes.
I think I once asked you that question. No, it's a good question, and it depends, as I said, entirely on inventory, as far as I can tell. And you're going to have high obliquity excursions. It's going to get warmer. That most of the sequestered CO2 will end up in the atmosphere. So I'd love to answer that question. I can't. It's the right question.
Well, how long do you need it to be present to
And need it in what
explain,
sense?
well, to explain whatever the unknown geochemistry, features, whatever features you really want to explain
Yeah,
with.
I've been trying really hard to avoid that trap because again, I see this as another possible mechanism for producing both morphological features and alteration features, but I'm not seeing it as a replacement for liquid water. So if the answer was some of the older minerals might have formed by this mechanism and the younger ones formed by water, I have no horse in that race. The only thing I can say is I don't think it gets any easier over time from a physics point of view, from an atmospheric physics point of view, to make liquid water than to make liquid CO2. I don't think it gets better. So I would say the age of the minerals speak for themselves, and one unlikely mechanism or another must have formed them. It doesn't really answer your question, but that's the point. We don't have answers.
Okay. Let's see. Any other questions here? So the lab studies will be um, a good sort of next step, and then you can kind of take it from there and see what else you can figure out.
I can imagine if we see reactions, even if it's just carbonate formation in the laboratory under plausible early Mars-like conditions, and even better, if we find characteristics, let's say, of those carbonates that allow them to be distinguished from carbonates formed by liquid water, I think then a lot of people in the community will sit up and pay attention.
Mm-hmm.
Okay, because now we have something that can be experimentally validated on Mars.
Now, remind us the earlier lab work that was done that kind of was, let's see, was Hoffman lab work? Or there were other papers that you pointed to that were lab work, I thought,
No,
for
no,
other applications.
the lab work is entirely in the context of the sequestration of
Yes.
liquid CO2
Yep.
underground. So it's all at room temperature, 20
Okay.
degrees C or
Okay.
above, up to say 100 degrees C on the high end, or even 120 at high pressures, moving towards supercritical. And while our colleague, and collaborator here, Sam Crever in Imperial College in London, has done quite a bit of this work, and he's starting to look at rate constants because, intentionally, now that he's aware of the Mars opportunity. And if you can determine rate constants under those conditions, you might be able to say something about plausible Mars-like conditions. But I think he's the only one working on that, to my knowledge.
Okay. Cool. Well, this is really interesting stuff. Again, very thought-provoking. Thank you so much, Mike. We appreciate your time on this, and good luck on the SSS.
Thanks. I think now that things are back moving again, after the shutdown, maybe we'll have some, some chance of hearing about this soon.
Yeah. Yeah.
Good.
Fingers
Anybody
crossed.
here who has any follow-up questions? I think you all know where to reach me.
Yep. Okay, good. Thanks again. I'm going to stop the recording.